The Cosmic Clash, General Relativity versus Quantum Mechanics. This is a tale of two titans in the realm of physics, each reigning supreme in its own domain. Our understanding of the universe rests on two pillars: Einstein's general relativity and quantum mechanics. These theories have revolutionized our comprehension of the cosmos and the microscopic world. General relativity beautifully describes the universe on the largest scales, governing the motion of planets, stars, and galaxies. It provides a framework for understanding the vast cosmic dance of celestial bodies. It paints a picture of gravity as the curvature of space-time caused by massive objects. This elegant theory redefines our perception of gravity, not as a force, but as a geometric property of space and time. This theory has been incredibly successful in explaining phenomena like the bending of starlight around the sun and the expansion of the universe. Its predictions have been confirmed by numerous experiments and observations. Quantum mechanics, on the other hand, reigns supreme in the microscopic realm. It delves into the behavior of particles at the smallest scales, where the rules of classical physics no longer apply. It governs the interactions of atoms, subatomic particles, and the fundamental forces of nature. Quantum mechanics reveals a world of probabilities, where particles can exist in multiple states simultaneously. Quantum mechanics has given us incredible technologies like lasers and transistors, and it accurately predicts the behavior of particles at the smallest scales. These advancements have transformed our daily lives and driven technological progress. However, these two foundational theories seem incompatible when we try to combine them. The smooth, continuous fabric of space-time described by general relativity clashes with the discrete, probabilistic nature of quantum mechanics. This clash is most apparent in extreme environments like black holes and the very beginning of the universe, where both gravity and quantum effects are extremely strong. In these realms, our current theories break down, leading to paradoxes and contradictions. Attempts to describe such scenarios using both theories simultaneously lead to nonsensical predictions, suggesting a fundamental flaw in our understanding. This has driven physicists to search for a deeper, more unified theory. This conflict highlights a deep mystery in modern physics. How can we reconcile the universe's grand, smooth fabric with the jittery, probabilistic world of quantum particles? The quest to bridge this gap is one of the most profound challenges in science. This question lies at the heart of the search for a theory of everything, a single framework that can encompass all the fundamental forces and particles in the universe. Such a theory would revolutionize our understanding of the cosmos, uniting the macroscopic and microscopic realms into a coherent whole. Strings to the rescue, a new fundamental picture. String theory emerges as a bold attempt to resolve the conflict between general relativity and quantum mechanics, two pillars of modern physics that have long been at odds. It proposes a radical shift in our understanding of the universe's fundamental building blocks, suggesting a new way to look at the very fabric of reality. Instead of point-like particles, string theory suggests that everything in the universe is made up of tiny, vibrating strings, each with its own unique vibrational pattern. Imagine these strings as incredibly small, one-dimensional objects, much smaller than even the smallest subatomic particles, almost unimaginably tiny. These strings are not made of anything in the conventional sense. They are the fundamental constituents of reality, the very essence of what makes up everything we see and know. Just like the strings of a violin can vibrate at different frequencies to produce different musical notes, these fundamental strings vibrate in different modes, giving rise to the particles we observe in the universe. This simple yet profound idea has profound implications, challenging our understanding of the universe and opening up new possibilities for scientific exploration. The different vibrations of these strings correspond to different types of particles, with their properties determined by the string's vibrational pattern, much like how different musical notes are produced by varying the tension and length of a violin string. For example, one vibrational mode might correspond to an electron, another to a photon, and yet another to a quark, each with its own unique characteristics and behaviors. In this way, all the diversity of particles in the universe emerges from the rich repertoire of string vibrations, painting a new and intricate picture of the cosmos and its underlying structure. The hidden tapestry, unveiling extra dimensions. One of the most intriguing and mind-bending aspects of string theory is its requirement for extra spatial dimensions. These dimensions are not just theoretical constructs, but are essential for the mathematical consistency of the theory. While we experience the world in three spatial dimensions, length, width, and height, and one dimension of time, string theory suggests that our universe may have additional hidden dimensions. These dimensions are beyond our everyday perception and understanding. These extra dimensions are not some far-off, inaccessible realms. Instead, they are curled up and compactified to incredibly small sizes, far below the reach of our current experimental capabilities. They exist at scales so tiny that even our most advanced instruments cannot detect them directly. Imagine a garden hose viewed from a distance. It appears as a one-dimensional line, but upon closer inspection, we see that it has a second curled-up dimension. This analogy helps us visualize how extra dimensions might be hidden from our view. Similarly, string theory suggests that the fabric of our universe may have these tiny, curled-up dimensions at every point in space. These dimensions could be intricately woven into the very fabric of reality, influencing the fundamental nature of our universe. The geometry and topology of these extra dimensions play a crucial role in determining the properties of the strings and consequently the particles and forces we observe. The shape and size of these dimensions can affect how strings vibrate, which in turn determines the characteristics of particles. The exact number and configuration of these extra dimensions remain an active area of research, with different versions of string theory proposing different possibilities. Scientists continue to explore these fascinating concepts, hoping to unlock the secrets of the universe's hidden dimensions. A symphony of strings, types, and their significance. String theory is not a single theory, but rather a framework that encompasses various different string theories, each with its own set of characteristics and predictions. These theories differ in the types of strings they allow and the specific ways in which the extra dimensions are compactified. One fundamental distinction lies in the type of strings, open strings and closed strings. Open strings have two endpoints, while closed strings form continuous loops. The endpoints of open strings are often thought to be attached to higher dimensional objects called D-branes, which play a crucial role in the theory. Closed strings, on the other hand, are free to move throughout the entirety of spacetime, including the extra dimensions. One particularly intriguing type of closed string is the graviton, the hypothetical particle that mediates the force of gravity. The presence of the graviton in the spectrum of string vibrations offers a tantalizing hint that string theory might be able to unify gravity with the other fundamental forces